This is our 3D printed, life-size wearable suit. With a motorized helmet, LED eyes, and LED gloves and chest, our suit is just like the movies. Lightweight and easy to take on and off.
Alright guys, this is our 3D printer, the Creality 3 EnderMax Neo. We got it for around $300 on Amazon at the recommendation of a YouTuber named Frankly Built, who is another cosplayer who does Iron Man and Batman type suits with 3D printers as well. As you can see, our 3D printer is currently printing a piece. It has a little user interface here. You can see the print time. It has been printing for 47 hours and it has 5 hours remaining. You can tune it, you can pause it, you can stop it, and it has some statistics here. The nozzle temperature, the bed temperature, the fan speed, and the Z offset as well, which controls how high the nozzle is. So the 3D printer moves in 3 different ways. It has the Y-axis, which is the bed, which moves back and forth on its own axis. It has the X-axis, which is the hot end, which moves side to side. And it has the Z-axis as well, which moves up and down. Additionally, you can see over here the spool of PLA, which is like a little plastic. It goes through here, through the tube to the hot end. The hot end heats it up and it comes out the nozzle and creates the file.
I'm about to show you. This is a program I use called Ultimaker Cura. You can get it for free on the internet, and basically what it does is it converts STL files into G-code files, which allows the 3D printer to read it and actually print the object. So you just go here, File, and then open your desired STL file. I open the faceplate one. You can do a lot of different things. You can move it side to side, up and down. You can rotate it even like that. But basically what you want to do is, once you get into your desired position, you will slice it. And so slicing it is what actually changes it from the STL into the G-code, and it adds the supports as well. And so this is going to take a minute to load, but once it does load, it'll display the time that it takes to print and the amount of filament it's actually using to print. And then it'll allow you to export it onto your SD card, which can be put directly into the 3D printer, and then it prints.
The most technologically advanced part of our project is Iron Man's helmet. Inside of the helmet are the LED eyes, 2 MG90S servos attached to lever arms, as well as 2 helper arms for stability. The LED eyes are hooked up to the circuit, so every time the helmet is closed, they will light up. At the crown of the helmet are the 2 servo motors. They are programmed to spin in opposite directions to open the faceplate. The lever arms are attached to a bracket and rotate 120 degrees to fully open the helmet. The helper arms provide stability when the faceplate is opened. Without them, the faceplate will concave inward and not be able to close properly. This was definitely one of the most challenging parts of the helmet because they require very specified placement for the helmet to open, as well as required more torque to open, so alterations to the helmet had to be made.
Okay, I'm going to go over the coding for our Iron Man project. All of our code was loaded onto an Arduino Uno board to perform the various actions we needed it to. All this code we downloaded from this website known as GitHub. This was linked to us through Frankly Built, who is the YouTuber we used for a lot of the insight into this project. How our coding works is it's linked to this circuit right here. How this circuit works is there's a 5-volt battery that connects to a button, an Arduino Uno, LED eyes, and servo motors. How the Arduino works is there's multiple pins attached to it, which has wires running through it, and how the code will interpret it will take from specific pins to perform specific actions. An example of this can be found right here in the coding, where it defines servo pin 9 and servo pin 10. On the Arduino board, there's a pin 9 and a pin 10 with wires running into it connected to the servos. For the most part, all of this code was fairly simple and we didn't have to alter any of it, and it worked with our configuration. The one thing we did have to change was right here where it defines the angles of the opening of the lever arms. So the full range of motion is 180 degrees, as said right here. All we had to do with this right here is we changed these values from 0 to 180 to 40 and 140, which basically just made it so the range of the motion of the lever arms was much less, and therefore the helmet could open without having to slam it into it. We were able to do all of this with this program known as Arduino IDE. Basically all it does is once you have all of your code uploaded, You can click right here and it will compile all of this code for you. Once it's done compiling, you can upload it with this button right here.
One of the main challenges of this project is just 3D printing in general. It's kind of an overwhelming task. With 3 different axes, it's difficult to adjust them all perfectly. As well, there's the bed, which is also difficult to adjust. On the underside, there's knobs, which adjust the height, and you have to find the perfect height to make sure the PLA sticks to the platform. It's a lot of trial and error and deciding which height works, and it's a difficult process.
Many of our prints also failed. This may have been 30 seconds into a print or 72 hours. The nozzle may have clogged, the unmelted filament may have snapped, or the filament may have not stuck to the bed. Sometimes we were able to salvage it, like this helmet here, but other times we were not. By the end of the project, I ended up with 3 full trash bags of wasted filament.
Many of the parts on our 3D printer also broke. We had to replace many nozzles because they became clogged with PLA. We had to replace the thermistor on the bed, which tracks the temperature. We had to replace the tube, which feeds the PLA into the hot end because it became clogged. We had to replace the conveyor belt on the x-axis, which moves the hot end back and forth. We even had to replace one of our hot ends. This is a new one we're currently not using because it started leaking with PLA. And I even had to replace the motherboard at one point.
Another challenge we faced was some of our objects being too large for our 3D printer. So for instance, this chess piece shown here was way too big for our printer. So we need to cut that in half. Unfortunately, Ultimaker Cura does not have a feature to where you can cut it in half, but I found another program called Idea Maker that does allow this. And so it has this feature called Free Cut. And so as you can see, it'll cut straight down the middle, and you can start cut, and it'll cut the model directly in half. And then you can export it into 2 different files. And so as you can see, it is 2 different pieces now. And then you'd export both of them into Cura to then be sliced to be printed. So one major challenge of this, besides the printing, was then reattaching these pieces. We used a combination of hot glue, super glue, and epoxy. Epoxy by far worked the best. It felt a little bit dangerous though. It smelled bad. It burned your skin if it got on it. Super glue was okay. It was kind of the in between, and then hot glue just really didn't work at all. And so some of our pieces do look a little janky, but it's because we had to slice them, unfortunately.
Putting all the 3D printed pieces together to form the suit was not as challenging as the rest of the project. To do this, we used elastic cords, nylon strap, buckles, as well as duct tape and foam. Combining all of these, we were able to make the suit wearable and comfortable as well.
At times, the 3D printer would print out 3 to 5 pieces in a row without breaking or stopping. This was extremely satisfying and rewarding.
Here are some of the lessons we learned from this project. To be completely honest, if we had to do it over again, we may have considered doing something else. 3D printing is frustrating and tedious. Teaching it to ourselves, printing everything out, putting it all together, and doing the electronics within a year was a difficult process. I've been non-stop printing since July, and I have broken pieces like this scattered throughout my house. Additionally, some of the pieces we are using aren't anywhere close to perfect. As a novice, I've realized that 3D printing is not a suitable long-term or large-scale project. But I have learned a lot about 3D printing. I know this model, the EnderMax Neo, like the back of my hand, in addition to the programs it runs with. I could diagnose pretty much any problem with it, and I feel very comfortable printing things in the short term. Yes, difficulties do still arise, but overall I've gained a lot of valuable information about 3D printing as a whole.
We also learned many effective wiring and coding techniques.
But most importantly, we learned many life lessons. Firstly, teamwork. We were constantly working together throughout the project, but we also divided up the tasks. I was mostly in charge of the 3D printing, while Owen was mostly in charge of the electronics. This way, we were able to work together, but also become experts at our individual fields. Second, communication. We were constantly communicating throughout the process. We were already friends prior to the project, so we felt comfortable communicating about what needed to be done and when. Last, accountability. We constantly held each other accountable throughout the entire project. If someone was gone for a weekend or didn't get their work done on time, instead of the other person picking up that slack, we held them accountable. We were not afraid to tell the other person to do work, and I think this led to our process being done in a quick and timely manner.